Hello, geodesy lover. We are going to talk about the two systems that are based on range differencing, aka Doppler. These are the Doppler-based systems. NNSS, Navy Navigation Satellite System, aka Transit, some people call Doppler system, and the DORIS, NNSS Transit is no longer available. DORIS is used. It is mostly for scientific use, as you're going to see. NNSS Transit, it caused the first big revolution in positioning, with some people claiming that it is a precursor to GPS. So let's talk about the system here that was so important, 1970s and 1980s. US Navy Navigation Satellite System, also known as Transit, it started operational in '64 for military service, then '67 for civilian use. It has a history. The objective of the system was to position these nuclear submarines, because a nuclear submarine would have to be underwater for a long period of time, and then to know the position they would have to go up to the surface and take shots at stars that a time when they would be vulnerable and they could be detected. So to avoid that, everything they needed was just to put an antenna up and outside of the water, so the submarine would still be under the water, under cover, and the antenna would then receive the Doppler signals transmitted from the satellites and get its position with 100 meters or something. That was good enough. Now, the civilian community, surveying and geodesy, they realized that they could use that, and they started doing it. More and more, the NNSS was used for establishing control, and also control at the geodetic networks. That was a triangulation network, and also control for surveying measurements. To get position at the decimeter or even centimeter level, you'd have to stay in the same site for several days, because the satellites, there are only 5 of those, or up to 7 at one point. They would not be available all the time. And why is that? Because they would not have the system was not intended to provide 24/7. Satellites in polar orbit, so different from GPS, 1,100 kilometers high, so it's much closer, which means that they travel over a particular point on the Earth much faster, 107 minutes. So the whole thing is you'd have your receiver, and then the satellite would come, a particular satellite would come, and you would observe it for some time. Well, 1 hour, a little bit more if the satellite's a zenith, typically less than that. And then you have a first set of solutions based on one satellite pass. And then you'd have to have another satellite would pass maybe a couple of hours later. So you have now a different satellite pass, a different geometry, and then another satellite passes. So it takes some time to really build up some redundancy. You could have a position with just one satellite pass at the 100 meters, and then you'd grow into the redundancy. So we require several days. Again, you could do that in a point positioning mode. That was the intent of the system. For us in geodesy and surveying, it was not good enough, of course, so we'd have to set up camp. And you could also establish baselines. Okay, that was a technique known as translocation. Transmitted two frequencies at 150 megahertz and 400 megahertz. Therefore, we could combine these two frequencies and generate a atmospheric free delay signal. Orbital information was superimposed on both carriers. There was no IGS to provide us with post-fit better quality orbits. And he used the Doppler effect. There are two series of satellites. One was the NOVA satellite, then the Oscar. This is the earlier one. These are the latest one. Some satellites are still in orbit, but no longer for geodesy. As we discussed before, people use that for monitoring these. We can use that for monitor satellites. You can use that for. What happens here is that the satellites are still in orbit. They still broadcast signals, and people use that for as extra signal for the study of the ionosphere and the space weather. The Soviet Union had a counterpart that's called Cicada. Okay, so they also had their own Doppler system. The guide to GPS positioning provides a good overview there. You can have a look. The idea of mentioning the transit system is because it has a very important historical aspect. You should realize that, for example, the transition to NAD 83 involved determination of Doppler points on the classical network. Okay, so they were used as constraints for the position of the center of mass, the origin of the coordinate system, and also for scale. Now we are talking about a system that exists. This is the DORIS system. DORIS, it is an acronym for Doppler Orbitography by Radio Positioning Integrated on Satellite. It's a French developed system. It has no military intent. Its objective is to offer precise orbit determination of satellites, other satellite systems that have DORIS receivers on board, and for positioning on the Earth. But it is an interesting system because the receiver is not on the ground. The receiver is on the satellite. On the ground, we have the transceivers, the transmitting stations. So it is, you have to think upside down. It is composed of onboard package the MVR receiver that measures the radio velocity. It has an omnidirectional antenna and an ultra-stable oscillator. There is a beacon network. These are the grounds, the transmitters, and there is a control and data processing center. It measures the Doppler shift on radio frequency signals emitted by ground beacons, ground stations, and received on board of the spacecraft by the receiver. It uses two frequencies. Here they are, which means we can also combine them to dramatically minimize the effects of ionospheric delay. That is also, we can also have these time tagging auxiliary data that can be superimposed. So the time reference of the DORIS time system, DTS, is provided by the master beacons. There are two master beacons, one located in Toulouse, France, and the other in Kourou, which is in the French Guiana, in South America, which are connected to atomic clocks. So they have to synchronize these two atomic clocks. For point positioning missions, the ground beacons may be installed according to different users' need. And they are self-contained with autonomous power supply. So what the French does is, if someone wants to have coordinates determined with DORIS, they would have to have these self-contained transceiver or transmitter. Would be transmitter. Transceiver is when you transmit and receive. So that's a transmitter. Installed where you want to have the coordinates. So that's why the system really haven't taken off, because you can do that much easier with any GNSS system constellation. So the data will be uploaded. The observations go from the transceiver to the satellite. They are stored in the satellite, and when the satellites go through Toulouse and Kourou, these observations are downloaded and then processed. They are essentially, at the end, they are processed in Toulouse, France. So the DORIS is more of a scientific system, because it's used for orbit determination of satellites that have the DORIS receivers on board. We can also look at variations in the Earth gravity field, monitor Earth rotation, and be used for precise positioning, navigation, timing. This is the global network of the DORIS ground stations, the ground beacons. We can see that I used to have one here in Ottawa, St. John's, Yellowknife, Toul. These are the three radio beacons located. It is much well distributed hemispherically than any other system, to be honest with you. If we look at the north and southern number of northern hemisphere stations and number of southern hemisphere stations, they're mostly equivalent. Here is a list of a few satellites that have onboard DORIS receivers. The Spot 2, this is for remote sensing. Topex Poseidon is for satellite altimetry. Spot 3, Spot 4, NVSat, these are remote sensing. JSON is satellite altimetry, Spot 5. So there are some extra information here, in these links that oh, I don't know if they work, but anyway, we have links here to these satellite missions, just explaining what they are. I think if you click in the PDF, I think it's going to work. And here is an example of a radio beacon in Ottawa. So we have here the antenna, the transmitter. Again, it looks like any ordinary antenna built thing. Okay, and so that's not UNB. Yeah? Looks like UNB, but it's not. That's in Ottawa, in a building that I think it was torn down already. The building on Booth Street in the federal capital. So until next time. Oh, by the way, there is a paper written by the folks from the international DORIS system that provides a nice overview about the DORIS system, and this paper is available on Desire to Learn. Another interesting thing is that these guys, people who work with DORIS, they meet every year, and the meeting has a very interesting name. It's called the DORIS Day. Okay, see you later.